So we are going to discuss transition elements. Okay. Uh, for the transition elements, of course, if you remember from IGCSE or O levels, we used to discuss the periodic table in which we have discussed like different groups, different periods, position of elements. Like we have, if you can see the periodic table. So this is just like that. Let's say this is going to be P block elements and this is going to be D, and on the lower of the periodic table, that's the F block elements, isn't it? So we are going to discuss today D block elements. Okay, we are going to discuss D block elements. More specifically, we will be discussing transition elements. We must know what is the difference between D block elements and also the transition elements. Okay. So first of all, let me tell you about the D block elements. D D block elements. So what is D block element? So I can say that let's suppose I'm going to tell you the proton number of any element. Let's say the proton number is 21. Let's say the proton number is 21. Okay. So when you will be writing an electronic configuration, that's gonna be, I can say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Okay. Then 3d1. As you can see, this configuration is ending on D block on the D orbital. So we can say this is the D block element. Okay. So those elements whose outer electrons are lying in the D orbital. So we can say that this is going to be D block elements. Same goes for sodium. Same goes for sodium. As we know that the proton number is 11 for sodium. If you will be writing an electronic configuration, so we can say 1s2, 2s2, 2p6, and then 3s1, as its like its outer electron is lying in s orbital. So we can say that this is an s block element, isn't it? That's the reason sodium lies on the left hand side. It's the s block element. S block element contains group 1 and group 2. P block element contains group 3, then 4, then 5, then 6, then 7, then 8. And this is the D block element. Okay. When you will be writing an electronic configuration for chlorine, let's say, whose proton number is 17, it's going to be 1s2, 2s2, 2p6, 3s2, 3p5, right? So it's going to be 3p5. As we can see, its outer electron is in the p orbital. So chlorine is going to be in the p orbital. And you know, the position of chlorine is on the right hand side. So this is the p block element. Okay. So after writing an electronic configuration, we can identify the position of an element, whether the element is present in S block, whether the element is present in P block, and whether the element is present in D block. Okay, so before going to do this, you need to know electronic configuration, right? In the syllabus, we are supposed to know the electronic configuration from proton number 21 to 30. This is called 3D series. This is called 3D series. So we will be discussing only period 3. Okay, like after calcium, then we will be discussing scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So we will be discussing this. So first of all, let me tell you about the D block element. Then I would be telling you. Basically, we would be revising an electronic configuration. So I'm supposed to write the definition of D block elements that I can say those elements I can say those elements, right, whose valence electron, or I can say outer electron, whose valence electron is in d orbital, is in d orbital, are called d block elements. Okay. So like I told you an example of, let's say, copper. Let's say, no, let's say, let's say scandium. Scandium, whose proton number is 21, right? So 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3d1. Okay, so as we can see, its outer electron is lying in the d orbital. So this is going to be the d block element, as its outer electron is present in d orbital. Outer electron is present in d orbital. That's why it's a d block element. Okay, so basically the configuration that I did is technically wrong, but I would be telling you later on. First of all, I want to tell you the introduction of the d block elements. Like, 4s comes after 3d. What's the reason? I would be telling you. But originally, this is the configuration. Originally, this is the configuration. If you remember that table, let's see this table. 1, 2, 3, 4, 5, 6, 7. Then 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 4, 5, 6, 7. So we have S, 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 S. Then we have P, 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 P. Then we have D, 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 D. And then we have F, F, F. Then I can say the first arrow is on 1s, the second arrow is on 2s, the third arrow is on 2p, the fourth arrow is on 3s, then the fifth arrow is on 3p, then next arrow is on 4s, next arrow is on, then the next arrow is on 4p, then the next arrow is on 5s, and then the next arrow is on 4d, okay, and then on 5p, then on 6s, and then so on, and then so on. So after looking at this pattern, I'm supposed to write, as we can say, I'm supposed to write like that. We can see one, like 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, then 3d10, then 4p6, and then 5s2, and then so on. In the syllabus, we are supposed to write down an electronic configuration from 1 to 30. So this is all about 30, right? This is the 30. We can memorize it as school, school, public school, public school, Daud, public school. Okay? School, school, public school, public school, Daud, public school. Since we know that s orbital is going to have 2 electrons, 2, p orbital is going to be 6, then 2, then 6, then 2, d is going to have 10, then 6, and then 2. So after writing this one, it would be very easy to write down an electronic configuration of all the elements. Okay, of all the elements. Remember, since as I have written electronic configuration for scandium, as you saw that, this is going to be 3D. You know what the 3 is going to represent? 3 means that this is going to be in the third period. This is going to be in the third period. And D means it's going to be in the D block. That's it. Okay. Let me tell you another example. That is, I say iron. Iron is 26. 1s2, 2s2, 2p6, 3s2, 3p6. 3s2, 3p6, then 4s2, then 3d6. Okay. Since again I can say its outer electron is lying in the d orbital, so it's a d block element. Okay. So same goes for s block element and same goes for the p block element, right? So after discussing the d block elements, so we have to discuss what are transition elements. What are transition elements? So let me tell you the transition elements. Transition elements. Transition elements. It's like the same. If you remember in IGCSE, we used to tell you what is the difference between base and alkali. Remember? Base and alkali. So we used to say base is insoluble in water, but alkali is soluble in water, isn't it? Base is insoluble in water, but alkali is soluble in water. The same goes for this one. And also we used to say all alkali are bases, but all bases are not alkali. If you remember, same goes for this one. All transition elements are D block elements, but all D block elements are not transition elements. I would be explaining this. I would be explaining this. But let me tell you the definition of uh, transition elements. So we can define transition elements as uh, those elements, like I can say, um, they are going to have they are going to have unpaired electrons. They are going to have unpaired electrons in their ionic state. In their ionic state. Okay. What do I mean by this? Ionic state. So let's say scandium. Let's say scandium. Scandium is 3 plus generally. The charge on scandium is 33 plus. Okay. So of course the proton number is 21. 3 plus means loss of 3 electrons. After losing 3 electrons, sorry, what would be an electronic configuration? So first of all, I am going to write the original configuration. Then I would be writing down the ionic configuration, right? So first of all, I'm going to write the normal one. That is going to be, I can say 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, and then 3d1. That's an electronic configuration, right? Then after writing down this one, I'm writing the electronic configuration of its ion, like I'm talking about plus 3. 3 plus. You know, very important thing is to know that when these elements will lose electron, so remember, electron will be removed from the 4s orbital first. Electron will be removed from the 4s orbital first, remember, okay? And then you can remove another electron from the 3d orbital. This is very important concept. Remember, right now I'm telling you this, okay? Whenever we will be removing an electron, so first of all, we have to remove an electron from the 4s, and then we have to remove an electron from the 3d, okay? So, so I have removed 3 electrons. two from S and one from 3D, isn't it? So it's 0 and it's 0. Okay, understood? Then what we have to see, after becoming ion, is there any unpaired electron? After becoming ion, is there any unpaired electron? You will say no. You will say no. There is no unpaired electron. There is no unpaired electron in 3D. Okay. So I can say there is no unpaired electrons. There is no unpaired electrons in 3D, in 3D subshell. So, so scandium 3 plus is not a transition element. Okay, so I can say scandium 3 plus is only D block element. It's not a transition element. Hopefully you understood the difference between the D block and the transition metal. D block element, but not transition element. Got it? It's very easy. Okay, it's very easy. Uh, okay. After scandium, then we have titanium. After scandium, then we have titanium. You know, titanium is proton number is 22. And let me tell you one thing, that's the reason all the compounds of scandium would be having white in color. It's very interesting. If you remember from IGCSE, we used to tell you that transition elements are going to form colored compounds. But if this is not a transition element, so of course, how it would be forming a colored compound? Common sense, isn't it? So if something is not a transition element, so it is not supposed to form a colored compound. That's a simple and clear concept. Okay. So I'm going to write down an electronic configuration for titanium. Of course, the proton number is 22. I am supposed to write 3D2. I am supposed to write 3D2. Okay. I'm supposed to write 3D2. And then the general charge on titanium is plus 2. The general charge on titanium is plus 2. General charge on titanium is plus 2. So what would be the electronic configuration? Of course, it's gonna be 4s0. It's gonna be 4s0, but 3d2. What I told you, you have to remove electron from the 4s first. Okay. For your ease, for your ease, I am going to write down electronic configuration like that. See this one? I'm going to change the position, but later on I would be telling you why I did this. Okay. For your ease, I'm going to do this one. Yep. Always remember 4s comes after then the 3D. Okay. And okay. And then like that. Yes. Okay. So this is going to be 4s0, right? Because I have removed two electrons from the 4s. Then you can see after removing two electrons, this is the D subshell 1, then 2, then 3, then 4, then 5, then 5. So it's going to be 1, then 2. As you can see, it has two unpaired electrons. It has two unpaired electrons. Okay, it has two unpaired electrons. Yes, yes, this is a transition element. Okay, this is a transition element, right? Because what I told you, in their ionic state, they must have an unpaired electron. If they have unpaired electrons, so that's going to be transition element. If not, so it's not a transition element. It would be only a D block element. Hopefully you're understanding this. Then we have scandium, titanium, then we have vanadium. Then we have vanadium. What's the configuration for, like, what's the proton number for vanadium? It's 23. It's going to be the same. It's going to be the same like that. Oh, it's going to be the same. Okay. Uh, okay. Yes. But it would be 4s3. Sorry. Mhm. It would be 3d3, right? It would be 3d3. That's an electronic configuration of vanadium. Since the general charge on vanadium is, since the general charge on vanadium is plus 3. Okay. General charge on vanadium is what? Is plus 3. So what do we do? For plus 3, what am I supposed to do? Uh, I would be removing 3 electrons like that. I would be removing 3 electrons like that. And the remaining configuration would be, uh, and the remaining configuration would be, this is going to be 2, and this is going to be 0, isn't it? I have removed 3 electrons. After removing 3 electrons, after removing 3 electrons, what am I supposed to do? Yes. Yes. Then we have to see it has 2 unpaired electron. Yes, vanadium is also a transition element. Okay. In the same way, you have to check all the 3D elements. Like I'm talking about from proton number 21 to proton number 30. Okay. Can you tell me chromium? Can you tell me about chromium? And if you remember, in AS, you have discussed the exceptional configuration of copper and chromium. You have discussed exceptional configuration for copper and chromium. Let's say, I would be telling it to you. Can you tell me chromium? Is this a transition element or not? I'm going to tell you the charge. General charge of chromium is plus 3. General charge on chromium is plus 3. Can you tell me, is this a transition element or not? Yes. If yes, so why you have to justify your statement? Why it's a transition element? Fast. I'm waiting. Fast.
Sir, yes, it is.
Why?
So basically, it's in a d orbital because d orbital, in the d block elements.
It's a D block element, but I'm asking, is this a transition element or not? There is a difference between the D block element and a transition element.
Yes, sir, because in this at least one it उसमें कम से कम जो सर वो है ना at least one stable ion होता है
Hmm,
partially filled के साथ
okay. Or
और उसके
anything
अलावा
else?
So can't we just say because it has an unpaired electron?
How many unpaired electron it has? How many unpaired electron it has? First of all, you have to write down the normal configuration. Okay. First of all, you have to write down the normal configuration. Then you have to remove 3 electrons. Then you have to remove 3 electrons from chromium.
Is it three unpaired electrons?
Okay, let me check. So first of all, I'm going to write down an electronic configuration of chromium that is going to be is 24. Chromium is 24. So the configuration for chromium would be uh, the same thing, but 1s2, 2s2, 2p6, 3s2, 3p6, and 3d4, and 3d4. Okay. Now, now the very important thing is to know the stability of orbital. Which orbital is more stable and which orbital is less stable. Okay, which orbital is more stable and which orbital is less stable. So I'm going to revise it. Of course, you have discussed this one. There are two orbitals which are more stable. Number one is full filled and number two is half filled. As we know that 3D orbital is going to have 10 electrons. 10 electron means it's full filled. It would be more stable. Whether it has three, like whether it should have 10 electrons and whether it should have 5 electrons. Okay, in both conditions it would be more stable, but right now it has only 4 electrons. Right now it has only 4 electrons. 4 electron means it's partially filled, it's unstable. Partially filled means it's unstable. You have to make it stable. You have to make it stable. So what I'm going to do, I'm going to donate, basically, I'm going to uh, donate one electron from 4s to the 3d. After doing this, let me explain it that this is partially filled, which is going to be less stable, which is going to be less stable. Okay, so that's the reason after donating one electron, then the configuration of chromium is going to be then the configuration of chromium is going to be 4s1 and 3d5. Now you can check it. It becomes half filled, which is more stable, isn't it? Also, after donating one electron, it becomes also half filled, which is more stable. So when the examiner would be asking to write down an electronic configuration of chromium, then you are supposed to write down this one configuration rather than this one. Even you are not supposed to show the movement of electron from the 4s to the 3d. Okay, so it's for your understanding. Okay, because we must know the stability of the orbital, whether the orbital is full filled or half filled. So we have only two conditions for the stability of orbital, whether the orbital is full filled or half filled. If it is partially filled, so if that's possible to make it stable, so then you are supposed to like donate electron, and that's it. Okay, right?
Uh,
Shamir, mute kar lo. Okay. And then after chromium, like after writing down an electronic configuration, since we know the charge of chromium, since we know the charge of chromium, that is plus 3. Since we know the charge of chromium, that is plus 3. So plus 3 means that it's going to be plus 3 means that it's going to be like that. I am removing one electron from 4s and two electrons from 3d. After removing it, 3 electrons, isn't it? After removing it would be having 3 electrons. Now I can tell you that I can say that it's going to have three unpaired electrons. Since it has three unpaired electrons, so it's going to be, yes, it's a transition elements because in its ionic state, it has unpaired electrons. Okay, so chromium is also a transition element. Okay, and what do we about copper? What do you think about copper, whose proton number is 29? Whose proton number is 29? And the general charge on copper is +2. What do you think about copper? If it's a transition element, so how many unpaired electrons it would be having? Yes. And the general charge on copper is +2, by the way. Yes. Then I'm going to tell you. Okay.
Why is it one
Basically,
unpaired electron?
one unpaired electron. Okay, let me see. Uh, so the first of all, the general configuration for copper would be uh, it's going to be 3D9 and 4s2. It's the general configuration of copper. Since we know that again, again, it's partially filled d orbital must have 10 or 5. 10 or 5. In both cases, it would be more stable. In both cases, it would be more stable, right? But now it's having 3D9, which is the condition of partially filled, which is less stable. What I'm supposed to do, I'm going to donate one electron from 4s to the 3D. Then after donating, it's gonna be uh, 3D10 and 4s1, isn't it? 3D10 and 4s1. So it becomes fulfilled, which is more stable. Okay. Then it becomes half filled, which is also stable. So we have made it stable, right? So this is an electronic configuration for copper. Now I'm going to write down an ionic configuration. Since we know that copper is going to have a +2 charge, so copper 2 plus. 2 plus means I have to remove electron from 3D and 4s. It's going to be 3D9. So 3D9 means that when I would be writing this one, I can say I can say 1, 2, 3, 4, 5, 6, 7, then 8, then 9. It has only one unpaired electron. It has only one unpaired electron. Okay, it had only three unpaired electrons. And that's why, yes, copper is also a transition element. Okay, that's the reason when you will see the compounds of copper, it would be colored, sometime blue, sometime black, sometime different color, okay, sometime yellow. So why? Because it's a transition element. But when you will see the compounds of scandium, so you will see all would be having white color, like colorless, I can say, because scandium is not a transition element, okay, in its ionic state. So, okay, let us check zinc. Let us check zinc. Zinc is 30. Zinc is 30. So the configuration of zinc is going to be uh 3D10, 3D10 and 4s2. That's in the configuration for zinc. So what's the charge on zinc? It's generally plus 2. Okay, after plus 2, it would be 4s0. 4s0. And then I can say 0 unpaired electrons, 0 unpaired electrons. So zinc is not a transition element. So zinc is not a transition element, right? So we have to identify whether the substance is a transition element or not. So zinc is not. Okay, zinc is not a transition element. In this way, you are supposed to like identify. And also you must know what's the difference between the D block element and a transition element. Okay. Or I can say that also you need to know about the d orbitals. In AS, we used to tell you only s and p orbital. That's it. But in A2, you need to know. In A2, you need to know how many d orbitals we have and what would be the shape and what would be the shape. Okay. So let me tell you about the d orbital. So d orbitals, d orbitals, right? So let me tell you about the d orbitals. We have five: dxy, dyz, dxz, dx square y square, and dz square. Okay, and dz square. So there are five orbitals in d subshell. Each orbital is going to have two electrons. Each orbital is going to have two electrons. That's the reason. That's the reason all together it must have 10 electrons. That's the reason behind it. Okay, because each orbital is going to have two electrons. Okay, so and then we need to know the shape of d orbitals. Okay, like a p orbital it was dumbbell, like s orbital it was spherical. So in the same way we have to know the shapes of like d orbital. You can see uh, d orbitals. You can see the d orbitals. Okay. Uh, okay. So, yep. Mhm. Where is the picture? Okay. Hmm. Okay. Yep. Yes. So as you can see, this is going to be the d orbitals, right? Examiner would be asking to draw. It's a part of syllabus. That's why This is mandatory to know these shapes. Okay. So, and then when we would be discussing about the complexes, then we would be explaining it in a more detail, right? As you can see, there are two set of orbitals. It's a one set, it's another set. I will be explaining later on. But right now, I would be telling you why I did this one. Like in the original configuration, it was you can see 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. I'm looking at this table. That's why I did this one. It's an original configuration. So D is coming after 4s, but in reality, 4s comes after 3d. So this is I have to explain. I can say that I can say that 4s 4s versus 3D. I can say that 4s versus 3D. You know, different orbitals have different energies, right? Okay. Different orbitals have different energies, right? So when you will see the energy of the and 4s orbital, so you will find a very minimum gap. Okay, you will find a very minimum gap. It's it's the energy gap between the 3D and the 4s orbital. You know, when I would be putting electron in 3D, when I would be putting electron in S, so there would be a very strong repulsion between 3D and 4s. I can say there would be very strong repulsion between 3D and 4s. As a result of repulsion, you know, 4s would be having a higher energy. As a result of repulsion, 4 would have a higher energy than 3D. Now you are thinking, sir, why it's not going downward due to the repulsion? It's a common question. Why they are not going downward? Why they are not going downward? Why it's going upward as a result of repulsion between this and this? The thing is that the thing is that in the lower side of 4s, we have other orbitals as well. Like we would be having 2p, we would be having 3s, we would be having 1s, we would be having 2s, we would be having 2p. So it cannot go downward because there are also some orbitals which are having electrons. There would be again more repulsion. As a result of this, it's moving upward. When it will move upward like that, so automatically it would be having a higher energy. That's why we can say 4s is going to have higher energy than the 3D orbital. And that's the reason in every configuration, whenever we can see, whenever we can see that whenever we can see S and D orbital, so we will be writing down 3D orbital first and then the 4s orbital. And that's it. Okay, it's quite clear, right?